Hi, welcome. We're going to be looking at lesson 3.5 today, discussing scatter plots and the lines that describe them. We're going to refer to them as trend lines. We're going to create and interpret scatter plots, and we're going to use trend lines to make predictions. Let's just take a minute and jot these vocabulary terms down, and as we go through the lesson, I want you to come up with your working definition of what they mean. Scatter plot, correlation, positive and negative correlations, no correlation, and trend line. We have examined relationships between sets of ordered pairs, and we have decided on whether they were a function or not. And we can look at a graph, a table, or an equation and determine that. A scatter plot is a graph where the points are plotted to show a possible relationship between two sets of data. It's an effective way to display some types of data, and we'll discuss which types. Example 1 says, graph this scatter plot. The table shows the number of cookies in a jar from the time they were baked. Now, we know if we have a linear function, the changes in the domain are constant. Changes are constant, up by 1. The changes in the range, number of cookies, depends on the time. We're down 8, down 6, down 3. This is not a constant change. So we can see it's not a linear function. We're going to graph them. The x represents the time. The y represents the cookies. And we understand the definition between, or the idea between independent and dependent. Time is always independent. The number of cookies depends on how much time there's been. We discussed that it's not linear. We can see a bit of a curve to the data. We know it's going to bottom out at 0 because that will be 0 cookies left in the jar. We just don't know what time that will be. We plotted the ordered pairs. We see that it's a bit of a scatter plot. This table, this is your problem, shows the number of points scored by a high school football team in their first 4 games of the season. We need you to graph the scatter plot using the given data. Again, think to yourself, 1, 1, 1, the games are independent. The score depends on the game. We see a constant change in game and a non-constant change in the score. Plotting the ordered pairs, we see data like this. Notice our x-axis or domain has to represent the number of games 1 through 4, but the score goes much higher. It has to go as high as 46 to see that third game score. When we talk about correlation, we are saying, is it positive? Meaning, think about a line. It has a positive slope. It's the same thing for a scatter plot. Do we see a positive slope? That's the same as a positive trend in scatter plots. We're going to analyze these. There's 3 types of correlation the data can have. In the case where our data seems to be increasing, let's say x were time, as time increases, whatever y is representing is also increasing. If both sets of data increase, we say that we have a positive correlation. Notice now, as time increases, the y values are decreasing. One value increases, the other decreases. We say we have a negative correlation. And we can see clearly that we could draw a line through this, a line that would describe what the data was doing. In the third instance, we see that we have no pattern. We have data all over the place, and we say that there's no correlation. Describing correlations from scatter plots is just that simple. Let's look at what's going on here. We're talking about visitors to the beach and daily temperature. As the temperature goes up, that's what's happening on the x-axis, the independent value. What are the people doing? They're coming to the beach. As the temperature goes up, the people go up. They're getting closer to the water so that they can cool down. The correlation would be referred to as positive. We look at this. You guys do this one on your own. Describe the correlation illustrated by this scatter plot. If you came up with a positive correlation, you're correct. As the years increase, the participants increase as snowboarding became a popular Olympic event. The years passed, the participants increased, and there's a positive correlation. Identifying the correlation you would expect to see between the pair of data sets. Now you're going to come up with the correlation without seeing the data. If the average temperature in the city and the number of speeding tickets in the city, the temperature goes up, do the speeding tickets go up? If the temperature goes down, maybe we're talking about ice and snow, do the speeding tickets go down? We're not going to see a correlation here. The number of speeding tickets has nothing to do with temperature, although we could probably stretch and say that on the snow, speeding tickets would go down, you would think, using common sense, but there should be no correlation between the data. Identify what you would expect here, the number of people in an audience and ticket sales. Well, if we sell more tickets, there should be more people in the audience. These two are directly related. As one goes up, ticket sales, number of people in the audience should go up, giving a positive correlation. And how about this one? A runner's time and the distance to the finish line. The longer you run, the less distance you have to the end. Think about this one. As time goes up, the distance goes down. Not the distance from the start line, the distance to the finish line. There should be a negative correlation because we're getting closer. This distance is diminishing as this time is increasing. How about a correlation here? The temperature in Houston and the number of cars sold in Boston. Well, I hope that instantly you see that these two things have nothing to do with each other. There should be no correlation between how hot it is in Texas and how many cars we're selling in Boston. How about this? The number of members in a family and the size of their grocery bill. Well, this one makes perfect sense, especially if they're teenagers, right? The more people that are eating the groceries, the more groceries we have to buy. Hence, the bigger the family size, the bigger the bill. As family increases, the grocery bill increases. We should see a positive correlation between the two. And what would you guess? A correlation between the number of times you sharpen your pencil and the length of your pencil. Well, the more we sharpen it, what happens? The shorter it gets. The length diminishes as we sharpen it more. One is increasing, the other is decreasing. We should expect to see a negative correlation. Now let's match scatter plots to situations. Choose the one that best represents the relationship between the age of a car and the amount of money spent each year on repairs. Age of car. Well, -4 years old. What's going on there? Throw that one out. Look at this one. 0 years old up to 6 years old. The cost of repairs increasing as the cost of the car gets older. This graph says as the car gets older, the cost of repairs goes down. Well, that doesn't make any sense to me. My vote would be for graph B, explaining that as we drive it, there are things that loosen up and need adjustment and maintenance, so the costs will be going up. The age of the car cannot be negative. We knew that. We threw that one out right away. This graph shows a positive correlation, so it could represent the data set. There will be a positive correlation between the amount spent on repairs and the age of the car. This is negative. Therefore, the graph we chose, graph B, is the best one. How about for this one? the relationship between the number of minutes since a pie has been taken out of the oven and the temperature of the pie. So on our domain, our independent axis, as time increases, what's going on with the temperature of the pie? It's going down. At 30 minutes, it's less hot than it was at 10 minutes. So that one would make sense. We don't know about negative time. We can't time travel. So this graph makes no sense. We can't go back in time to before we put the pie in the oven or when we took it out. And this graph says, as time increases, the temperature of the pie is increasing. Well, it says we've taken it out of the oven. The pie should not be getting hotter. Graph A is the only one that makes sense. There you go. That was Check It Out example 4. Now we know that we can graph a function on a scatter plot to help show a relationship in data. Sometimes the function is a straight line. This line, called a trend line, helps to show the correlation between data sets more clearly. It can also be helpful when making predictions based on data. Let's look at this situation. Concession stand and the total number of tickets sold at a movie theater. Based on the relationship, predict how much money will be collected at the concession when 150 tickets have been sold. Well, let's look at the tickets sold, 20 up to 60. We have data for a little less than 60. What we want to do is make a prediction. This is 100, 120, 140, 160. We want to make a prediction for 150. So right through there, we want to figure out what that Y value or concession sales value would be. So picking the value 150, moving up to the line and over to the y-axis, we can make a really good prediction. $750 is a reasonable prediction for 150 tickets being sold. You guys try this one. Based on the trend line, predict how many wrapping paper rolls need to be sold to raise 500. So it's a relationship between wrapping paper and money raised. Rolls sold, money raised. So rolls is independent. The money we raise depends on that. We want to make a prediction. We want to raise $500. So go to the y-axis, money raised, 500. Move over to the graph. Find your line of your function, your scatter plot, and move down to rolls sold. Halfway in between 50 and 100 should be 75 rolls. Based on the data, 75 wrapping paper rolls is reasonable prediction for raising $500.